Okay, section 20.2 is about nuclear stability, and we're kind of starting to answer the question of why are some nuclei stable while others are radioactive. So a little bit about how nuclei work at all. If you think about it, protons are positively charged, and so protons should be strongly repelling each other. And yet a nucleus of a large element will take dozens of protons and cram them together into a tiny, tight area. And so there is something that's overcoming those tremendously strong repulsive forces. And that is what we call the strong nuclear force. And in physics, there are only a few forces. Ultimately, everything breaks down to either the gravitational force, or the strong nuclear force, or the electroweak force, which is like magnetism and electricity. The attractive and repulsive forces between positive and negative charges are all part of the electroweak force. And so what is the strong nuclear force is kind of like saying what is gravity. It's a fundamental force, but we can say, so we can't really explain what it is. It simply is. But we can say how it acts, and that is that it is a strong attraction between protons and neutrons. So the neutrons are like the glue that holds the protons together in the nucleus. Protons want to repel one another, but they're so strongly attracted to the neutrons, which are also a part of the nucleus, that the strong nuclear force overcomes those repulsions and holds a nucleus stable. You can have too many neutrons, though. If you have too much glue, too many neutrons, well, the neutrons aren't attracted to each other. The strong nuclear force is only between protons and neutrons. And so too many neutrons and it becomes unstable as well. A nucleus will be radioactive, or it will fall apart if there are too many neutrons. And so nuclear stability all has to do with having the right number of protons and neutrons. And there are some pretty interesting there are some pretty interesting trends that come out of this. So we'll talk about maybe the weirdest, most interesting and unusual things first, and then we'll kind of condense everything down into a simple rule of thumb. But first of all, if we look at all of the stable isotopes, and there's a finite number of them, we know them all and we can tabulate them, we can see that the overwhelming majority of stable isotopes have both an even number of protons and an even number of neutrons. There's a modest amount that have one of those numbers even and one of them odd. And then there's remarkably few stable isotopes where both the proton number and the neutron number are odd. Now this might seem really strange at first, but what it really suggests is that protons and neutrons pair up. They form some sort of pairwise interactions that are beneficial to stability. And so that's the first thing. The next is magic numbers. So magic numbers is a terrible name, but it has to do with these certain special numbers of protons and neutrons that seem to be particularly stable. And there actually is a precedent for this. If we look at ions and stable ions, well, they will tend to have certain numbers of electrons. They might have 2 electrons, or 10 electrons, or 18 electrons, or 36 electrons. If I look, for example, at oxygen 2-, fluorine 1-, magnesium 2+, sodium 1+, all of those have 10 electrons. And that's because they're isoelectronic with, hold on, is it neon? Anyway, the row 2 noble gas. Right, and so those could be called magic numbers for electrons and ion stability. And they have to do with the fact that electrons are organized into these shells, that the S subshell and the P subshell together will fill up when you have a noble gas electronic configuration. And so the magic numbers for ion stability are not all that magical once you understand the structure behind them. Well, nuclear magic numbers are also not magical at all. I hate that name. What they really are they're just numbers which are dictated by some energetic structure. And so, again, talk to the physicists about this if you want to know more particulars, but basically, there are models for nuclear energy levels, just like our SP, D, and F electronic energy levels. And those energy levels lead to certain numbers of protons and neutrons that are more likely to be stable. Okay, one sec. Let's get the next slide up. Okay, so the simplest and most important idea in nuclear stability is what's called the belt of stability. So figure 20.5 shows that. If we again plot all of the stable nuclei on this number of protons on the x-axis and number of neutrons on the y-axis, you can see that all of the stable nuclei follow a kind of a curve. It's not a perfectly straight line. There is some curvature to it, but you have roughly similar numbers of neutrons and protons with a little bit of an excess of neutrons. That seems to be the formula for a stable nucleus. And we can look at any particular isotope and we can locate it on this chart and see whether it's likely to be stable or whether it has too many neutrons or whether it has too many protons or too few neutrons. So nuclides that are above this belt, that are in the too many neutrons category, are likely to decay through beta decay. Beta decay will get rid of a neutron and add a proton, so that's going to push it down on this chart closer toward that belt of stability. Nuclides that are below that belt are going to undergo alpha decay, which loses two neutrons and 2 protons, and so it doesn't affect the ratio very much, but it will move. Oops, I'm a little backward here. Okay, it will move the isotope down in a diagonal fashion that will eventually intersect with that belt of stability, because the belt of stability has some curvature and alpha decay would be a straight line. So anyway, you don't even necessarily have to locate the element on this chart in order to determine whether it is above or below the belt of stability. Because our atomic mass numbers on the periodic table are based on natural abundances, and natural abundances are based on the stability of isotopes, we can just compare a particular isotope mass to the mass on the periodic table. So let me show you what that might look like. So if we pick some examples from, oops, what have I done? Sorry, here we go. If we pick some examples from yesterday, like U-238 that undergoes alpha decay. If I find uranium here and I click on it and I look at its atomic properties, oh, that's no good. Let's look at thallium. Okay, so we have thallium-210. Uh-oh. Yeah, that's right. Thallium-210 will undergo beta decay to form lead-210. That was one of our examples from section 20.1. And if we look at thallium's atomic mass on the periodic table, you can see here that it is 204.3833 grams per mole. So the stable isotopes of thallium have a mass number of about 204. But the thallium we were looking at, 210, has a higher mass than that. And so that higher mass is going to put it in the realm of having too many neutrons. And we'll get rid of that periodic table. Okay, it'll have too many neutrons and undergo beta decay to push it downward toward that belt of stability. If we look at something like, there aren't a lot of alpha decay examples that aren't just way out of line here. Let me see if I can find a good one. Well, we did have fluorine 18. Now, fluorine 18 actually technically underwent positron emission, but we can still kind of look at it in a theoretical sense. So fluorine 18 has an atomic weight of 18.998. Fluorine's atomic weight, based on natural abundances, is almost 19 grams per mole. So fluorine 18 is below that. It's going to be below the belt of stability, and you might imagine fluorine 18 undergoing alpha decay. The reality is it seems to undergo positron emission, which is much less common than alpha decay. So it's an exception to the rule, but if we were to follow this methodology, we would have guessed that fluorine 18 would undergo alpha decay. Okay, let's go back to the belt of stability. So there's one last little thing, and that's that there are predictions based on magic numbers and such models for nuclear energy levels, nuclear energies. There are models which predict that there might be an island of stability for elements that are further out even than the current periodic table. There may be elements that just have never been generated under natural conditions, or at least not that we've discovered, but which are stable and may someday be generated in high energy particle colliders and such. Of course, right now, particle colliders make all sorts of exotic particles that will decay within 5 femtoseconds. But these models predict that there might be stable elements, yet unknown, that could be discovered in these particle colliders that are stable enough that they can be recovered and that they can even be studied in chemical reactions and things like that, which could be kind of exciting. Okay, I better stop it here. So that's section 20.2 about nuclear stability.